Okay, so we have a groundbreaking lesson in two ways today. One, for you, you're getting introduced to a thing called logarithms that you've never heard of before until this moment, unless you've been in a math contest this year, at which point I would say sometimes things like this has logarithms in it, so you don't know how to do it. It's about as much as you got. Be careful there, because you're going to tip that box.
Okay.
The second reason it's logarithms, my word, I lost my word. Something breaking.
Groundbreaking.
Groundbreaking, thank you. Groundbreaking is in my YouTube career. This is landmark video number 600, is what I'm today.
Booyah!
Yay, 600. But first I have to introduce you to something that leads you to logarithms. So, you've never seen an equation like this and been asked to solve it. An equation like this is called an exponential equation. Anybody have a theory on why that's called an exponential equation? It has an exponent, but you've seen stuff with exponents before, but you've never seen one where the exponent is a variable. That is new to your life. So if you ever have an equation where the exponent is a variable, what you have for yourself is an exponential equation. And so you can't solve that unless I teach you about a new math thing. And that new math thing, that's the word of the chapter, is logarithms. What logarithms are, they're the inverse of exponentials. So where we're trying to get, not today, but where we're trying to get in the next day or two is to be able to solve equations like these. Because I was kind to you, there's two of these that you could solve right now based on math you know how to do and make sense. Can anybody solve one of those three?
First one is 3.
First one is 3. Because 2 times 2 times 2, 3 2s, makes 8. That's solvable because that's artificially easy and I was kind to you.
Well, the last one's 4.
The last one is 4. Because if we go 2 times 2 times 2 times 2, we will get 16, that is 4. But you can't solve this without some new kind of math appearing in your life. It just can't be done right now. You could figure out that this answer probably is between 3 and 4, and it's probably closer to 3, but it's going to be a number like pi, called an irrational number. It would never end, and it would never repeat. It's going to be a really weird number like that. Okay, so this is going to be 3 point something that goes on forever, but we can't do that yet. But that's where we're trying to be able to get is, no matter what the setup is, even if I get a little meaner than keeping it on powers 2, that you could solve it. That's what this is for. Question about that. So let's go flashback down memory lane. I'm going to blow your brain up a little bit the way old things blew your brain up, but eventually you adapted. At some point in your first math life, somebody taught you this. Things like this. 2 plus 3 is 5. And at some point they broke the news to you, if you can do this problem, you can do other problems in what's called its fact family by some people. They took your knowledge of this and blew your brain up for a day, but your brain eventually was like, oh, I'm okay with this. Anybody know what I'm driving at here? There's another way you could express this idea, just with different symbols, but it's in the same fact family. 5 minus 3 is 2. Or 5 minus 2 is 3. So they taught you adding, and once you had your mind wrapped around that, somebody broke the news to you, oh, okay, there's this other thing called subtracting. It's the same fact, we're just using a new symbol and like doing it inside out. Then eventually they broke this news to you, that 2 times 3 is 6, and you're like, oh, more symbols. And then they got around, after you got your head wrapped around multiplication, the idea that in the same fact family, it's true that
6 divided by 3.
6 divided by 3 is 2. Or, and that wasn't a new fact, it was just like there's a new symbol involved. And they like turned the tables on you. At some point, you learned things like this. And then at some point, somebody turned the tables on you. The root of 25 just gets back to 5. And all of these things go together in the same families because one is simply the opposite of the other. It's just expressing you the fact like inside out, but nothing is really new. So our first job today is going to be to just wrap our heads around, instead of expressing stuff with adding, express stuff with subtracting is an old skill. Your first skill is, instead of subtracting stuff with exponents, subtract stuff with the word of the day, logarithms. So log, 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 log. We're going to just use the word logarithm instead of an exponent appearance. We're just going to recreate the problem. Are we trying to do the math? No. We're just trying to rewrite the problem in like a different sort of a way. So old words will help us here. What was this called? That is called the base. When we do logarithms, this little number that's burrowing down into the ground, if you look around the board, you see these little numbers, they're called subscripts. They're burrowing down into the ground, like the opposite location of exponents. Those are also called the base. So whoever was the base is still the base. We're going to put that little number down underground. There's going to be an equal sign. X already had its turn. So whose turn must it be? Y. Okay, so X got to be the answer for this, so Y gets to be the answer for that. Kind of like what we saw over here, if we're still on the camera, 5 got to be the answer. So when you reverse it, 5's all about being in the problem. 2 and 3 were all about being in the problem, so now one of them gets to be the answer. There's just like a little bit of a switcheroo of who's in the problem and who is the answer. And then the other thing we're just left with, the only other thing is X. If you were typing this, log, X, and Y would all be at the same level in the same font. Same size, Times New Roman 12, all on the same line. This base would be a little bit smaller size and it would stash like down into the ground. Question about that reversal? Let's do it again. It's easiest, I think, to squat the base first. The base here would be 2. The base here would be 10. The base here would be 16. Squat the base and just put that like down underground. Question about that?
Why 16?
16 was the base for the power, so 16 is the base for the log. And once you get the base squatted, just take the other two numbers and go switchies. Since 8 was alone, 8's in the problem, which makes X be alone. 0.001 was a 1. So instead, it's in the problem. And the alone person is the -3. 16 was in the problem. So now, oh wait, no, 16 was the base, sorry. 1/4 was in the problem. So now, it's alone. And this must be the 2. We're just doing switches. Now it seems more confusing than it did when I did the subtract, add, root, like flipsies. But you'll get used to it. It's the same thing. It's just got you a new word instead of a new symbol. We're just doing the problems inside out. Questions about that? 100% worth a reminder that negative powers have a job in the world. What do negative powers do?
They swap signs.
No, don't switch signs. They flip things upside down. So 10 to the third means 10 times 10 times 10, which gets you 1,000. But a negative power flips that, so it's 1,000th, and that's a decimal equivalent of 1,000th. But you 100% want to either make a mental note or a note on your paper. Negative powers flip things. That is going to keep coming up through the chapter. Negative powers do flipsies. We just had that on the final. It didn't go away. What do fraction powers do?
They like do the opposites of
It's like a square root.
It's square rooty stuff. So this is, another meaning of this is index of 4, root of 16. You do need to continue to maintain the knowledge that fractional powers are roots. Roots and fractional powers are the same thing. That's in there. If that's new news to you, write that down somewhere. If that's old news to you, make a mental note anyway. Question about our first inside-out operation? So then let's go the other way. If I give you a logarithm problem, you should be able to make an exponent problem out of it. So who to the what makes what out of this? 2 to the 5th is 32. I think it's still easiest to continue to look for the bases. If the base is 2, the base is 2. 5 had its moment in the sun to be alone. So it's 32's moment now to be alone. And the 5 becomes a power. And if they do stick with numbers, all of the numbers situations they create need to be true. So if you think 2 times 2 times 2 times 2 times 2, that is 32. If you wrote this, that should strike you as dumb. 2 times 2 times 2 times 2 times 2 times 2, you're going to do 2 times 2 times 2 times 2 32 times and get 5? Like, there should be a pretty good giveaway there that that's dumb. 5 to the 2 makes 32. Well, that's dumb. 5 to the 2 is 25. So if they stick to all numbers, which sometimes they do, just make sure the numbers are like making a thing that seems like it makes sense with numbers. This one doesn't have all numbers, so that doesn't necessarily help us, but we can still go. Somebody to some power makes the third number. So what's up with this one?
The power of y.
It'll go 3 as a base to the power of y equals 5. That's true. The 3 was the base, so keep it the base. 5 wasn't alone, so now it is, and then the y's got to go somewhere. Last one, who to the who is what?
10 to the power of negative 2 is
10 power negative 2
0.01.
is 0.01. And that absolutely makes sense, because what did we just talk about negative powers doing? Flip it. So 10 to the regular 2 is 100. 100 flipped is 100th. And that is absolutely in the 100th place, so yeah, we're winners there. That's skill 1, that's the main skill of the day, is be able to just translate one world into the other and get used to this new world called logarithm. Question about this column before I stroll left and put my cameraman to work? All right. So the next skill after that is give you an equation that's in logarithm world and ask you to solve it. At some point in your near future, may not happen today, you might be able to just do this in your mind by like translating in your mind and just doing it. But I would suggest for today, do the translation probably on your paper. You're going to feel more comfortable. Looking at this is going to make you feel uneasy for a day or two or forever. I don't know when that switch will flip. But re-express this in exponent notation, just like we were doing. Who to the who is what? 2 to the negative 3 would equal x. And then figure out what 2 to the negative 3 is. What is our best answer for 2 to the negative 3?
1/8.
1/8 is correct, because negative powers for the third time today need to flip things. So 2 to the third is 8, flip C, 1/8. Who to the who is what? 10 to the 4th is x. You catch a break again, because x is alone again. Just math it, 10 to the 4th. Use buttons if you need to, but 10 to powers is nice. It is 10,000. If 10's the base, just put the zeros, 4 zeros for 4 powers of that. 2 to the who is what? 2 to the x. 16, that's a different kind of setting. We have to think in a different way, but we already did this within the last 10 minutes. It was 4 over there. It hasn't changed in the last 10 minutes. You may find yourself in this homework sometimes using your fingers. 2 times 2 is 4 times 2 is 8 times 2 is 16. 4 fingers means 4. Fingers are your friend. About that. There'll be another section in the homework, I think it'll be titled Compute. If you want to keep doing everything the same way, you could write on here equals x, and do it the same way. I'm gonna choose not to do that, but if you need to do that, do that. There's nothing wrong with the compute section, putting an equals and putting an x and running through the same stuff. This, you'd be doing who to the who is what then? 3 to the x is 27. What I'm gonna do is, what I said a minute ago, bust out my fingers. We're going, this is the base. I just need to do threes, lots and lots of threes. Figure out how many threes it's gonna take me to get to 27. I don't need the equals x personally to do that. And I don't think you do, but if you want it, do it. Put an equals x, do the rewrite. I have no criticism of that. But I'm just gonna sit here and go 3 times 3 is this, times 3 is that, times 3 is that, and I'm gonna use fingers till I land on 27. How many is that gonna take? 3. 3 times 3 is?
9.
Times 3 again?
27.
27. So 3 fingers, answer is 3. This, I'm just gonna sit here and go who times who times who times who?
10 times
10 times 10 times 10 times 10, till I land on 1,000. How many is it gonna take me? Also 3. Question about those? Here, what am I gonna do? Who times who times who times who? 5 times 5 times 5 times 5 times 5s, until eventually I land on 625.
Let's go 4.
It is 4. It's 5 times 5's
25.
25, times 5 again is a little bit over,
125.
it's 125, a little bit over 100. Go again. You're gonna hit that with 4. This we're trying to do
9.
9 times 9 times 9 times 9. Eventually you'll land on 729. 3 is correct. And I'll pause there because the next one goes a little bit weird. So here you're trying to go who times who times who? 9 times 9 times 9 times 9. But land on 3? That's not going to go that well. Okay.
No.
But it can be done. Can anybody do it?
Is it a third?
It is not, but that's not bad. It is a half. Fractions are a good thought, because for the second or third time today, what have we had about fraction powers? Fraction powers do roots. 9, if you do the root, makes 3. Rooting is half power. If you're not following that, do this. Put an equal x, like I said, you invisibly could anytime you want. And then we're thinking 9 to a power makes 3. For 9 to make 3, the only way 9 can make 3 is if you're doing a root. What's the exponent on this that's unwritten? 1. What's the index on that that's unwritten? 2. That is a 1/2 power. 1/2 is the answer to that. What math are we thinking here? We're doing who times who times who times who?
4.
4. 4 times 4 times 4 times 4 times 4. We're trying to land on 1/16, which is difficult. It is -2. Because if there's fractions, it's because we flipped it. What's for the 4th or 5th time today, flipping is caused by negative powers. So 4 times 4 is 16, so there is a 2 involved, but it's flipped, so it's a negative power that did a flip. This one's also a little weird. It is 0. We're thinking 7 to a mystery power makes 1. And that's a basic fact from way early in the year. Anything to the 0 power makes 1. That's a thing. A question about that? Negative powers flip things. So if we're trying to do 4 times 4, 2 of them handle the 16. But that got flipped. It's not regular 16. That got flipped upside down to make 1/16. Negative powers flip things.
Thank you.
You're welcome. Question up to there. Save the easiest thing for last, and by far the easiest thing. Question about where we got. I'll say this. The better you are at exponent stuff, the easier the logarithms are. So if you're like, I don't know about these fraction powers still, those give me a little bit of nervous hiccups. I don't know about negative fraction powers, like, if you're jittery on that, we'll need to fix that. But If you're solid on your negative powers, your fraction powers, all the powers we've done, then it's easier to adapt to the logarithm like. Then the final thing, okay, again, logarithms and exponent stuff are, magic word,
Opposite.
opposites. Just like adding and subtracting, or multiplying
And division.
divide. So if I gave you a problem like this, that would not concern you at all. That's an easy answer of x. Because the adding and subtracting are opposites and they just like wipe out. If I do x times 3 and then divide by 3, that's an easy answer of x, because the multiply 3 and divide 3 things just vaporize. If I go into this same problem and I'm doing 2 to a power with a base of 2, and I'm at the same time doing a logarithm with a base of 2, the base of this and the base of that are a match. I step in there and I'm doing 2 to powers and logarithm base 2. There's the same kind of nullification. The easy, quick answer is simply 5. Because there's no one else home. That's all there is. So if over here I hadn't said x, but I had said 74, you'd have said 74. So if I drop you in this world and I'm like 10's the base going to a power, and 10's the base for a logarithm, you just shoot me back a t, because all that other stuff just wipes each other out. If I write those inside out, same concept applies. This logarithm has a base of 5. This exponent has a base of 5. Those are just complete opposites, and your answer to this is 37. And your answer to this
32.
is 32, because there's just a wipeout of all the other stuff. At its heart, adding is an easy link to subtracting. Exponents are an easy link to logarithms. You just have to wrap your head around this, and hopefully the homework helps. The difficulty is adding was easier than exponents. So subtracting is easier than logarithms. But trying to make the jump, it's the same jump. Okay? So once you've dominated adding, you can dominate subtracting. If you already dominate exponents, you're ready to dominate logarithms. If your exponents are dicey though, we need to work out the 4 key things. Negative powers, flip. Fraction powers, roots. Anything to a 1 power,
0.
itself. Anything to a 0 power, 1. That's like your 4 basic side ideas, other than the ability to go 2 times 2 times 2 times 2 times 2, you know, and count fingers. But negative power split, fraction power is root, anything to a 1 itself, anything to a 0 is 1. If you know those are going to appear, but they're going to appear inside out. So if you're uncomfortable to begin with, and then I turn you inside out, you're going to be doubly uncomfortable. But that's the ideas. Question about ideas? We're in 12.3. I don't do 12.1, I don't do 12.2. I just jump in on 12.3 in this chapter. 12.3 homework's on 517. There's a 1 to 40. Some of you like when you can get it done in class. In 18 minutes, you could do 40 of these in 18 minutes. I guarantee that. So if that motivates you, jump on it. If you're wiped out because it's May, I understand. But if you've got some juice in you, there is time enough to get this done in time.
Can I borrow a book?
Sure.